Hello, everyone, and thank you for joining us for this webinar. My name is Matt Baxter, and I'm with the CCIX Consortium Marketing Work Group. And I want to thank you all for joining us today for this webinar. So without any further delay, I want to go ahead and turn it over to Millind. Millind, thank you very much for joining us today.
Okay, thank you. So good morning and good evening, everyone, if you're in a different time zone. So let's get started. I have put together a few slides that give an overview of the architecture framework for CCIX. So the first slide is again just touching upon why did the consortium was formed. Essentially, looking at from use cases point of view, what was the industry need that basically brought this consortium together. So there, I mean, the quick recap really is this, that as we all know that now the performance improvement that we can get out of general purpose processors year over year, the rate of that growth is slowing down. And also there are new applications that I'm showing on the right hand side, some examples, essentially some scenarios where now you have increased need for processing. The workloads are requiring specialized processing, right? And also there are workloads that require lower latency. So with all of that, essentially the industry is moving towards evolving platforms to become more easier to use heterogeneous architectures, essentially evolving platforms where you can deploy accelerators in a way that is easier to utilize the capabilities of the accelerators. And so the net of that is really the where we want to move to is that where you can now augment computation and memory with different architectures or different SoCs in a way that is consistent with the software view, where you want to see them as just a NUMA socket in your platform. So the two use cases that we enable, we want to focus on are, number one, is a use case of acceleration, where we are essentially want to augment the computation resources with a specialized task optimized processors. And basically from the usage point of view, your use paradigm is still similar to a multi-core usage paradigm, where you can easily offload a processing thread or computation to the accelerators, and they can work with the shared data structures with the host processors. So second is system memory expansion. The new memory technologies are coming about, like storage class memory, different types of DRAM technologies, and we want to allow augmentation of your system memory pool with memories attached via SoCs. So, and the other dimension behind, in addition to computation and memory augmentation, is improving the speeds and the latency attributes of the underlying transport that is utilized. So these are some of the drivers that the CCIX Consortium brings together. Next slide. Now I'm going to have a few slides on overall architecture framework. So here on the right hand side, essentially you see different building blocks that at a high level, these building blocks that bring the overall approach together. So the bottom gray box, think of that as really the transport. This is the carrier of the coherency messages or the basically load store messages with certain attributes, right, over a physical transport. Here this transport for CCIX is grounded in PCI technology, and I'll talk about that a little bit further. And then above this transport, we have this notion of a coherency interconnect that essentially allows you to construct communication between the requesters and the memory targets in a fashion similar to how in a multi-core processor architecture the communication happens between the different processors and memory targets. So there is essentially upfront we have taken a overlay network approach, where at top level you think of you're stretching out your coherency interconnect to span across these accelerator SOCs, right? And then from carrier or transport point of view, you're carrying the messages in optimized fashion over a transport which is grounded in PCIe for this generation. So first, again, if you look at the key blocks, you have a protocol layer, which defines the coherency protocol, read writes to memory, and it's really a full-featured protocol. If anybody who's familiar with, their proprietary internal processor SoC protocols, it essentially is, will look very familiar. And secondly, if you are familiar with CHI specifically, then this protocol will quite familiar. We also have at a protocol layer done some additional features to allow essentially utilization of multiple transport level interconnects to essentially allow for a seamless approach for high bandwidth interconnect between SoCs. So then after the protocol layer, there is this other building block, which essentially takes these messages, load store messages or coherency messages, and then maps them over to the transport formats, right? It could be for this generation, we are grounded in PCIe. So there's a set of things that are done there to carry these coherency messages as PCIe TLPs. And then below that, you have this transaction layer for the transport, and then the physical layer. So one of the things you will see here is that in the transport, we have essentially taken an approach where we left the PCIe transaction layer the way it is today for carrying normal PCIe traffic, but we have essentially required implementations to have implementation of two virtual channels. And the second virtual channel is what we call a C6 virtual channel, where the transaction layer is optimized to only carry a subset of PCIe messages, TLPs. Specifically, they only carry VDMs, vendor defined messages, right? Or there is a flavor of that can be carried if you have point-to-point connection. I'll talk about them a little bit further, and Bruce will get into specifics also later. So then physical layer, essentially, we have done enhancements here to support speeds that are not part of PCI spec today. For example, 25 gig speed, which is from PHY point of view, is a sweet spot beyond 16 gig. Next slide. So here now we go a little deeper in defining, what are the building blocks within the coherency protocol layer that need to be understood in order to follow the protocol. And Bruce definitely will get into a lot of details of those. So key, components to define coherency is some of these building blocks are you need a request agent, which you can think of as essentially a processor core with an L2 in front of it, which becomes the initiator of a request. A home agent, this is a point of coherency for a given address range. This is essentially which enforces coherency across multiple copies of a cache line. Slave agent is essentially a concept of behind a home agent you have a memory controller, but if that memory controller is across the C6 link, then that is essentially a memory controller that is across C6 link is referred to as a slave agent for a home agent. Error agent is essentially an addressable entity that is used for logging error messages. So this will become more clear as Bruce goes into the protocol definition. Next slide. The last point I want to emphasize before I pass it on to Bruce is that in C6 architecture, we leverage PCIe for transport, right? So from the point of view, and as a result of that, we also benefit from essentially getting all the management infrastructure support for managing C6 components. So now, because PCI is a transport, then on the PCIe virtual channel, we essentially view a PCIe topology, which is a tree topology in case of PCIe. So that is one aspect that holds. Even though from PCI VC point of view, we are seeing a tree topology, in C6, we enable constructing non-tree topologies from the point of view of communication of load stores and coherency messages between the requesters and the targets, right? The home agent or the from home agent to a slave agent. And the way the flexible topology and routing is enabled at the coherency layer is by having our own namespace for addressing the initiators and targets, and having our own routing tables for routing the coherency messages across the topology. So some examples of the topologies here are direct connect. You can have actually a PCI switch in the middle, and that is also enabled because PCI, this is will come up, I think, in coherency protocol discussion. Bruce will get into some details there. And then we have flexible topologies like fully connected mesh, and it could be just connecting with the host, the mesh, or just amongst themselves, and then through processor you can connect over PCIe. That's all I had for providing the overview of the architecture framework. Bruce, you can take it from here, unless so Matt, for questions, answers, you want to wait till the end, or should I take some questions now?
Shall I push ahead with the coherency protocol overview, and then we can take the Q&A session at the end?
Okay.
So thank you very much, Millind, for the introduction and the framework. I'm now planning to talk you through the C6 coherency protocol, and I hope to take 50 to 60 minutes in order to do that, and we will then allow hopefully 10 to 15 minutes at the end for some Q&A, some questions and answers. So during today's session, I'll start off with a very high-level overview of coherency and why we need it. I'll then go in to talk about each of the different agents that Millind's outlined, so the request agents and the types of requests that they issue, the role of the home agent in the system. I'll briefly talk about slave agents and where they fit in, and then we'll go on to look at some of the lower level details, so the crediting mechanism that's used, some of the message formats, and how we pack those messages together into packets. So let me start off at the very highest level, talking a little bit about what coherency is and why we actually need coherency in a system. So the fundamental principle with system level coherency is that it's simply caching data in multiple places in a system. The diagram here illustrates a request agent that has some form of cache, and it's accessing memory through a home agent where that memory is remote on a separate chip. And the standard principles of caching apply in that we get a performance improvement whenever we reuse data items that are held in the cache. So whether that's multiple accesses to the same bytes within a cache line, or whether that's accessing different locations which are located close by within the same cache line, whenever we get that reuse, the data held in the cache gives us a performance improvement by giving a reduced latency and reduced power consumption access. So the thing about system level coherency is that it allows caching not only at one point in the system, but at multiple points. And as the diagram shows, there may be two or many more request agents in the system. So let me now go on to talk about how the actual coherency protocol works. And it's all based on having a set of states for each of the cache lines that exist in the system. So each of the caches on the previous slide is broken down into a set of different cache lines. And for each of those cache lines, in order to implement a coherency protocol, we give each of those cache lines a particular state. So essentially, there's 4 states for any cache line that's held in a cache, and a cache line that isn't in a cache is considered to be in the invalid state. Within the CCIX protocol, those cache line states can actually be considered in a 2x2 fashion. So a cache line will either be in a unique state or a shared state. When a cache line is in a unique state, that guarantees that it's only held in that cache, and there's no other copies in other caches in the system. And that's nice because it means that the line can be read and updated within that cache without notifying any of the other agents in the system. Or alternatively, the line may be in a shared state, and when a line is in a shared state, that means that it may be held in other caches in the system. It's not a guarantee that it's held in other caches, but it may be, and therefore it's necessary to notify other caches in the system before any changes are made to that cache line. So that's one axis. In the other direction, a cache line can either be clean or dirty. So dirty is pretty much what you'd expect from a normal cache. When a cache line is dirty, it means it's been updated with respect to main memory. And before the cache line is evicted, the main memory must be updated to hold the new value. In fact, in the coherency protocol, when the cache line is evicted, you can either update main memory or you can pass responsibility for that cache line onto somewhere else in the system. It's just important to make sure that at least one agent maintains responsibility for updating main memory before the cache line is eventually removed from all of the caches. So a clean cache line is slightly different. A clean cache line doesn't mean to say that it's exactly the same as memory. It may be that the value that's held in the cache line is different from memory, but it means that this particular cache is not responsible for updating main memory. So when a cache line has been changed, the same value will be held in multiple caches. One of those caches will hold the line as dirty, and all of the other ones will hold it as clean. So just to run through the 4 states, so you can see them labeled here: unique dirty, shared dirty, unique clean, shared clean. Throughout the rest of this presentation, you may hear me using just simply the 2-letter acronyms. So UD, SD, UC, and SC, and it's simply just referring to the cache line states. So just for completeness, I'll talk about the fact that the protocol does support partial cache line support. And that is 2 additional states that allow partial cache lines to be held. One is a unique clean empty state. That's where a particular cache has permission to store to a cache line, but it doesn't actually hold any data. And associated with that is a unique dirty partial state, which is where the requester associated with that cache has written to some of the bytes in the cache line, but not all of them. So it's partially dirty. The main reason for highlighting this is partly to talk about, in order to give a complete overview of the cache states, but also to highlight the fact that there are a number of features in the protocol which are optional features, as is this particular feature, and we use properties within the protocol in order to indicate whether or not a component supports that feature or not. So as part of the discovery and enumeration process that happens when first setting up a system, it's necessary to go around and to discover some of these properties. Obviously, they all have sensible default values. And then the system can be configured in order to enable a particular property if it transpires that all of the connected components can support that property. So with that, I'll move on to just talk through some examples of the coherency protocol. I think this is just a useful way to show how the particular cache states interact with each other, and hopefully it gives a good feeling for the operation of the protocol. In these examples, I've shown 3 different components: requester 0, requester 1, and requester 2. They each have associated with them. Hopefully you can see a cache. It's just a few lines. Obviously the cache lines are fairly random addresses, and with each of those cache lines there is some data associated with it. And talking through these examples, I'll use address 1000 as the one we're interested in, as that's the traditional address to use in these circumstances. So let's start off with an example where requester 1 in the middle wishes to read location 1000, and I'll step through some animations. So hopefully you'll see these appearing on the webinar as we go. So requester 1 issues a request to address 1000, and that causes the system to look into the other caches that are available. And obviously we'll talk about this in a lot more detail later on. And where data is found, then we can move a copy of that data to the other cache. And then just to add on to this, both of these caches would then be held in the shared clean state, so we can see how the cache states are used to indicate the state of the cache line, and each cache will know that another cache has another copy of that line. If I then move on with this example and say, let's imagine we've got to a point where the same cache line is now held in all 3 caches, and it's in a shared clean state in all of them. And now, for example, R0 wishes to write to location 1000. So the first thing that R0 will do is to issue a transaction. It knows it needs to do that because it holds the line in a shared state, so other caches need to be notified. The coherency interconnect, or the home node more specifically, home agent more specifically, knows that it needs to go and send transactions, Snoop transactions to those other caches. So it will do that and cause those to invalidate the cache line, moving that line to the invalid state. That means that now R0 has the line in a unique clean state, and because it has it in a unique state, it can then go on and update that line, and we can see that the value in the line has changed from 1, 2, 3, 4, 5, 6, 7, 8 to the new value, AA, BB, CC, DD, and the state of the line has moved to UD. And finally, to complete the sequence, if we now show R1 coming back and attempting to read that line again, it will do the same thing. It will issue a transaction, a request to address 1000. That will look in the other caches as appropriate. And when that cache line moves across to R1, we see the data value being moved across. And now R0 keeps responsibility for updating main memory. So it has the line in the shared dirty state, and R0 now has the line in the shared clean state. In fact, the protocol permits moving the responsibility for updating the memory to R0. That's just one of the options that are available. This is just illustrating one example of the flow. Okay, so I'll now go on to talk about primarily the request agent and all of the different types of requests that it can issue into the system in order to perform different operations. Broadly, these break down into read transactions to obtain a copy of data, write transactions which are passing a dirty copy of the data elsewhere. There are some atomic operations which actually perform an operation on a particular location. And finally, we've got a group of dataless transactions which manipulate the cache state in other caches in the system without actually passing data to or from the requester. So I'll go through each of these groups with a slide or two on each of them, and we'll talk through what these transactions are and how they're used. So I'll start off with read transactions. There's lots of different ways of breaking these down and grouping these, but broadly speaking, we can think about a set of coherent read transactions, which is the first 3 groups here. They are all transactions that will go and snoop into other caches, look in other caches for the data that they wish to obtain. But maybe I'll just talk first of all about the transaction at the bottom, read no snoop, which is used for accessing non-coherent memory. So that's memory that's not shared between different caches. And primarily it's used for accessing peripheral devices. whereby the data for a peripheral won't be held in a cache, so there's no need to go snooping caches in order to perform the access. So a read no snoop, that can support various ordering models and various memory types that I won't talk in detail about today, but obviously there's lots more information on that in the spec. And I'll come back to the three groups at the top of the slide. So first of all, we've got read unique. That's used when a request agent wishes to write to a cache line, and the read unique transaction is used to obtain a unique copy of the line. The next three, read clean, read not shared dirty, and read shared, they're all used when a request agent simply wants to read a cache line. So when reading a cache line, it doesn't need to have a unique copy, it just needs to make sure that other copies are notified that that this cache is going to have its own copy. So they will, the home will process that transaction in an appropriate fashion, and we'll look more about the snooping that can occur later on. The difference between these three transactions is the permissible states in which the cache line is returned. So, for example, a read clean is guaranteed to return a clean copy of the line. Read not shared dirty will return a line in any of the cache states except shared dirty, and so on. The read once clean invalid, and read once make invalid transactions are all used for taking a snapshot of data. I'll just say at this point that read once clean invalid is sometimes called Rocky, and read once make invalid is called Romy, just slightly easier to say. So all three of those, read once, Rocky, and Romy, they all take a snapshot of a coherent location. So that means that the requester that's obtaining the data guarantees not to cache the data that it's been given. It's just a single use version of the data. And that's typically used by I/O coherent devices. The Romy and Rocky versions are actually used to control the cache state of the line after it's been accessed. So that's just a hint, but it can be used to hint at deallocating the line, which, for example, might be used where a cache line is being egressed from the system. It's being sent out on a network interface, and it's known that nobody else is going to want to use that line. So there's some hint that can be used there in order to influence the allocation policy in the system. So that's a coverage of all of the read transactions. I'll move on now to talk about the write transactions. And again, maybe I'll start at the bottom with write no snoop. That's very similar to the read no snoop that we saw on the other slide. Obviously it's a write transaction, but it's used for accessing peripherals, and it can also be used for accessing non-coherent memory, so memory that's not shared between caches. And again, it can support different transaction sizes and ordering models and memory types. Of the coherent writes, there's actually four principal flavors. There are other aspects to this, such as whether or not it's a full or partial cache line write, but I won't go into that level of detail today. I'll just stick at the high level here. So I'll start off with write back. A write back is used for moving a dirty cache line towards main memory. The line is deallocated after that transaction is completed, and this transaction is typically used when a cache eviction occurs. So a capacity eviction requires the cache line to be removed. The next one on the list is write clean. That's similar to a write back, but the requester actually keeps a copy of the cache line. This is typically used when a cache line is being cleaned, and so that may occur for something like persistent memory. If you have non-volatile memory and you wish to make sure that the non-volatile memory is updated with all of the latest writes, then you would clean the cache lines, and that would result in a write clean operation. Right, third on the list is the write evict transaction, and that's slightly different from the other two because write evict is used to move a clean copy of a cache line to a downstream cache. That is a cache that is closer to the memory, typically a system level cache. A write evict is not needed, is not functionally required. It's an optimization, that can be used when evicting a clean cache line, and it allows a cache line to be passed around where it's thought that it could be useful to maintain it within a cache in the system. There's actually some controls in CCIX in order to influence when the write evict transaction is used, to make sure that it's only used at times that it's going to be giving some form of performance optimization. And then last one for this slide is write unique. This again is a transaction that can be used by an I/O agent that's not keeping cached copies. So it's a single write to a cache line. The write unique is guaranteed to snoop the other caches in the system and make sure that no other copies make sure there's no other copies, so that the write will update the value that's held in memory to make sure that all of the caches are coherent and up to date. So that's the write transactions. Next one I'm going to talk about, the next major group, is the atomic operations. So atomic operations are transactions that move effectively move the operation towards the data. So things like incrementing a location in memory, rather than pulling in the value that's held in memory into a cache, updating that value in the cache, and then pushing the updated value back out towards the memory. An atomic operation allows that operation to be moved towards the memory and for it to be executed there. So that's a more efficient use of the data movement. The other advantage of atomic operations is that where there are multiple agents that are all trying to perform an operation on the same memory location, you can sequence those atomic operations and they're all guaranteed to make progress, so they don't suffer from some of the retry attempts that you need to do with things like exclusive accesses or load, link, store conditional type operations. So so the atomic operations are more efficient for performing particular operations on memory. There is a list of the operations at the bottom of the slide. I'll come back to those in a second. And within the CCIX protocol, we've defined 4 primary groups of atomic operation. The first one is what we refer to as an atomic store. That moves data with the operation from the requester to the memory. That's shown on the top right-hand side of the slide. And that completes with just a simple small response back to the requester to indicate that the operation has completed. The next group that we have is the atomic load, where the requester sends out the operation as previously with the atomic store. But in the case of the atomic load, there's also data sent in the opposite direction as well, back to the requester. The important thing to note about the atomic load is that the data that is returned is the original value of the data before the operation happened, rather than the value of data after the operation is completed. The motivation for doing that is that actually back at the requester, that means that the requester will have both, will be able to calculate both the value before and after the operation. If the atomic operation only returns the value after, then in some cases where the operation is not easily reversible, it wouldn't be possible to determine the original value. So the other 2 atomics that we support are an atomic swap. So that simply swaps a new value for an old value. And then the final one, slightly more complex, is where there are 2 outbound values. It's referred to as an atomic compare. More fully, it's a compare and swap operation. So 2 values are sent out. One value is compared with the value held in memory, and if their compares match, the swap value is swapped into the memory location. So the operations for the atomic store and the atomic load, where there are operations that can be performed, there is a list here of the 8 operations that can occur. So we've got an add or increment. We've also got a set of logical bitwise operations, so bit set, bit clear, and exclusive OR, bitwise exclusive OR. And there's some arithmetic operations as well, so max and min operations for both unsigned and signed data values. For the arithmetic operations, there is support for both big and little endian data formats. that is provided in the operation, and so it can operate on either a big or little endian data structure. But I don't intend to discuss the finer details of the big and little endian data structures in today's webinar. So finally, for the requests, we come on to the dataless operations. It's quite an interesting group of different types of operations. So there, I'll walk through the different use cases that are available. This isn't an exhaustive list. It's just trying to give you a good feeling for when we use these types of operations. So first on the list we have clean unique and make unique, and that is used when a requester already has a copy of data, so it doesn't need to be given any data, but it wants to take a line from a shared state to a unique state so that it can perform an update to that line. So a clean unique transaction will clean all other copies of a cache line and remove and make sure that any dirty copies that exist elsewhere in the system update main memory. And a make unique is simply used to force removal of all other copies of the cache line. In the case of a make unique, any other dirty copies are discarded, and so a make unique transaction is only used when it's guaranteed that the request is going to update every single byte in the cache line. So the next group of transactions are the cache maintenance operations. So we have clean shared, so that's used for cleaning out all of the caches. So for a particular address location, you can ensure that all caches are cleaned. For clean invalid, that is used to perform both a clean and invalidate of a cache line. And finally, there's make invalid, and that performs just an invalidation. So those three operations are typically used when software cache maintenance is being used. It's an interesting combination here, because these transactions are used where a system is using both a combination of hardware coherency in order to maintain coherency between cache lines, but also for some particular memory regions, it may be using software managed coherency as well. And that's where these transactions are used to software manage coherency with other agents that may not be part of the coherent subsystem. The next transaction is clean shared persist. That's really another form of cache maintenance, but that's a particular form that is used to ensure that a dirty cache line has been updated in some form of non-volatile memory. And the response to that transaction is only given when the cache line is persistent, and that means that the update has been made to persistent memory, and it's guaranteed that the line, the updated value, will still be visible, still exist in that memory after some power cycle has occurred. So if the power is removed, either expectedly or unexpectedly, then the line is guaranteed that it will be visible after that. Last on the list for the dataless, and also last of the transactions that I'm going to talk through, is the evict transaction. So that is used to notify a home node or Snoop filter. So I'll come on and talk about the home node and the Snoop filter shortly. But that's used when a request agent wants to notify that it no longer holds a copy of a cache line. And as we saw earlier, and we'll see later on as well, that's important to work out who's going to get snooped. So that can be a useful piece of information. Okay, so I finished talking through the request agent and all of the different request types that it can perform. So I'll now go on to talk about the role of the home agent in the system. And effectively what the home agent does is that it's responsible for controlling the cache states of all of the caches in the system when a particular line is accessed. For any single address in the system, there is one identifiable home that is responsible for that address. Typically each home looks after a range of addresses, but for any one particular address, it's clearly defined which home agent is responsible for that address. The home agent is expected to have some mechanism by which it can determine which of the request agents in the system hold a copy of that address. It may be a Snoop filter or directory or any form of structure that's very much implementation defined about how that structure is built. There's lots of different implementation options. So you can build home agents that have very precise tracking of which request agents hold a line. You can build structures that have a more coarse granularity, and you can also have structures which may track, track precisely when there's a small number of sharers of a line, and maybe track less precisely when there's a large number. But anyway, lots of different implementation options. So as I said, when a request agent tries to access a particular line, the home agent is responsible for knowing which other caches it may exist in. It will send Snoops, as shown in the diagram, to each of those caches to manipulate the cache state in each of those request agent caches. And I'll talk a little bit later on the next slide about the different Snoops that can be sent. The home agent is also responsible for collecting the data, typically for a read transaction anyway, where the home is returning data. It will either get that from one of the cache copies, and sometimes the home agent will access main memory when it doesn't have a cached copy that it can use. So the diagram shows it accessing 3 out of the 4 request agents here. Typically, it's expected to be less than that, but it could be many agents. It could be all of them. The home agents, the protocol, does support a broadcast mechanism for snooping all of the request agents when the home agent doesn't have a precise definition of who has a copy of the cache line. So on this slide now, we're looking at the home agent and the use of Snoop transactions. So down the right-hand side of the slide, you can see the list of all of the different Snoop types that are available. They're all used to manipulate the cache state in the different request agents. You may well hear me use the term Snoopy. So as in the second bullet point here, a Snoopy is effectively a request agent that's being snooped. So we'll use that terminology. One thing I just wanted to highlight is that the specification talks about expected behavior and permitted behavior. So typically when a snoop occurs to manipulate the state of a cache line, there is what is considered to be a best or most optimal behavior from a performance perspective, and that's typically the behavior that we would expect, typically the state transition that we would expect. But there are other permitted behaviors. So those permitted behaviors are things where it's functionally correct, but it may be less optimal from a performance perspective. And so any implementation of a Snoopy can choose between the expected and the permitted behaviors. It may well be that some designs choose to make a design simplification at the cost of a performance a trade-off, and depending on the nature of the component, that may well be the best implementation choice. So looking down the Snoop types that we have, as I said, they're used to manipulate the cache state in the Snoopy. So first on the list we have Snoop to I, so that forces the Snoopy to the invalid state, and that's used when the original requester is trying to write to the line. The next one we have forces the line to the shared state, or one of the shared states, so that's Snoop to S. And that's used when another agent is trying to read the line, to get a shared copy of the line. The Snoop to SC Snoop is used specifically to force to the shared clean state. We have a dedicated Snoop for that, because although the protocol supports the shared dirty state, it also supports the ability to effectively avoid the use of the shared dirty state. Shared dirty state can be slightly tricky to track in the home agents, because if you're trying to track both a number of different sharers and also which one holds the dirty copy, that's obviously more information. So some implementations will choose to avoid that, and when they get a dirty copy, they'll either make sure there's just a single dirty copy, or they will clean that out to main memory and have multiple clean shares. Snoop to C, that moves the line to a clean state. I talked earlier about a non-volatile memory, and so that's again an example where we'd be using Snoop to C to obtain any dirty copy of the line, push that out to non-volatile memory to make sure it's persistent. Snoop to any is that what the name means there is that there isn't any required cache line state change. So the receiver, the Snoopy, can leave typically it would leave the cache state exactly as it was prior to the Snoop. So Snoop to any is used to obtain a snapshot of the cache line, the current version of the data, but there's no need to change the cache line to a different state. Finally, to complete the list, Snoop make I forces a line to the invalid state. So what I haven't talked about in this slide set is that for each of these particular Snoops, the specification defines not only the cache state changes that are required to occur, but also the data transfer. So, in cases where the line's being invalidated, if there's a dirty cache line, you'd expect that to be transferred. There are other cases where it's requested that a clean copy of the cache line is provided. And Snoop make I is a particular, an optimization, if you like, and that forces the invalidation of a cache line without returning a dirty data. And we talked a little bit about the use cases for that earlier. So just to complete the agent discussion, we've talked a lot about request agents and all of the different requests that they can issue. We've talked about the role of the home agent and looking after snooping in a system. A slave agent is used to provide additional memory for a home agent. The diagram here shows a couple of request agents and a home agent on one chip. A common case is that the memory is actually provided on the same chip, and in that case, the slave agent isn't specifically CCIX visible as a protocol visible agent. However, the protocol also supports memory expansion, and so it's possible for a home agent to use memory that resides on another chip, and that is accessed through a protocol visible slave agent, which is typically the memory controller for that additional memory. Okay, so I finished the discussion of all of the different agent types. So I'll move on in the second half of the CCIX protocol overview to talk a little bit more about some of the topologies, some of the crediting mechanisms, the message formats, and the packet formats that we use. So let me start talking about topologies. So we specifically call out 3 different topologies that are supported. They're not the only ones that are supported. I'll talk a little bit more about that in a second. But these specific topologies are described. So first of all, we've got the fully connected topology, and that's where every agent is connected to every other agent. I should say every chip. This diagram, the circles on this diagram are indicating chips. And the black lines between them are indicating CCIX links connecting those together. So in the fully connected case, every chip is connected to every other chip, which obviously makes the routing nice and easy. It's always simple to know which direction you have to go, and there's no need for any multi-hop message routing. The next topology is the tree topology. Those familiar with PCIe will be very familiar with the tree topology. Again, I mean, so it's certainly a simpler topology in terms of routing. One of the characteristics of the tree topology is that if you break any one of the links, then the topology effectively falls in 2. So there's no possibility to build any loops in this topology, and hence it's easy to avoid any deadlock conditions. And then finally, we have the multi-dimensional array topology. So that in this, the diagram illustrates a 3 by 3 2-dimensional array. There's no restriction on the number of dimensions or in terms of the number of agents in a particular, in any one of those dimensions. So lots of possibilities are available in terms of building that array. There are some special considerations with the multi-dimensional array in terms of some of the packet routing, and I'll come back to that. I'll touch upon that in a later slide. These, as I say, these are the three primary topologies that are mentioned and described. The reason that these topologies are pulled out in the specification is that for all of these there are known deadlock-free routing algorithms. So there are ways of building the routing such that there's no loops which can form deadlock conditions. There's nothing in the protocol that prohibits building other topologies that are deadlock-free. So there's no restrictions to other topologies. It's just that these are pulled out as being ones that are known good topologies. So talk just a little bit about message routing. So two primary forms of message routing that occur in the CCIX protocol. The first is address-based routing, and this is used in the first instance when a requester initially issues a transaction. So each of those transactions that we saw earlier, the reads, the writes, atomics and dataless transactions, they all have an address field in the request. And the protocol uses a hierarchical address decode. I should just mention that actually there's two forms of address routing that occur. So there is effectively one set of routing for request agent to home agent requests, and another set of routing for home agent to slave agent requests. I'm not going to be diving into any more detail on that today. Just wanted to highlight that those two forms exist. Probably of more interest is the fact that because the address routing is done on a hierarchical basis, what that means is that on each individual chip, it's only necessary to do the address decode to route any message to the appropriate CCIX port and link on that chip. So when designing a chip with a given number of ports and links, just to sort of dive just a little bit into that. So what we're expecting is that a port is effectively a set of physical pins, and within a port there can be multiple C6 links within that port, and multiple links are used when you're routing through something like a PCIe switch. So all that's needed is an address decode that identifies both the correct port and link in order to make it to the next chip, and then at the next chip another hierarchical address decode is performed. Once the address has reached the home node, from then on ID-based routing is used to complete that transaction. So any response back to the original requester is done using the agent ID of the requester. If there are any snoops that are needed, then the home agent will identify the snoopies that need to be snooped by their agent ID, which was obtained when the original request for their copy was sent. And any snoop responses that are coming back to the home after snooping has happened is also done on ID-based routing. And just a note on the slide that there are special considerations for snoop response routing when operating in a multi-dimensional array topology. Okay, so that's the message routing. I just wanted to briefly touch upon the agent ID space, the agent ID namespace. So as I said, that is used for routing the messages. Routing is done based only on the agent ID, not the agent type. And because of that, there are some rules associated with allocating the agent IDs. So the whole process of discovery and enumeration, which occurs at the initial system bring up, needs to allocate the agent IDs. I won't talk through that process today. There are some follow-up webinars that should describe that process in far more detail. But just to give you an overview of some of the rules, you can see here on the slide, different agent types with the same agent ID must be in the same chip. So we've got some examples here, RA0 and HA0 living in the left chip. Moving across, we've got RA2 and HA2, also RA5 and HA5 again. All of those must be in the same chip, and RA4 and HA4. But the other thing to note is that there's no requirement for the agent ID values to be contiguous on a chip. So, for example, one chip has agent IDs 2, 3, and 5. Another chip has agent ID values 4 and 6. So the expectation of the routing table, the ID-based routing table, is that it's structured in a way that it doesn't need to have contiguous agent IDs associated to a particular route. Okay, so we've looked a little bit about the different topologies, and we've looked at the types of requests that are going backwards and forwards. So I just wanted to touch now upon the crediting mechanism that's used. So in C6, the crediting that's used is a link-based credit mechanism. So before any message is sent, then it's being sent to some buffers that exist on the other side of the link. So the diagram on the right-hand side here is trying to illustrate that. So what we see is that when we're sending messages across from the left-hand side to the right-hand side, there are some buffers, some resources that are on that side, and those messages are only sent when there's space in those resources. That's what the credits are for. And in C6, we identify 3 separate types of credit. There is request credit, data credit, and Snoop credit. It's illustrated both in the text and the diagram. There's no requirement for the number of those credits to be the same for the different credit types. And when any message is sent, it will require a certain number of those credits. So a read request or a dataless request requires just a request credit. A write request or an atomic request requires both a request credit and a data credit, because obviously they're sending data alongside the request, so it requires both of those credits to be available before the request is sent. And then finally, there's a Snoop. If a Snoop is going to be sent, it requires a Snoop credit. There's no explicit credit for any responses. So any transaction responses or read data responses or Snoop responses, they don't have explicit credits associated with them. It's the responsibility of the agent that is sending the request to make sure that it can guarantee that there is space for the response that is being received. So that keeps us down to the credits illustrated. In terms of when credits are being used, so as messages are being sent and using up the resources, as those resources later on free up, obviously the credits need to be sent back. And there's 2 forms of doing that. The credit return can either be done in a piggybacked fashion, where it's sent alongside other messages. So small numbers of credits can be piggybacked on other packets containing other messages. Or there's a dedicated credit exchange message, and that's used for sending large number of credits all in a single combined message. So just for completeness, I've highlighted on the bottom of this slide that there is an additional miscellaneous message within the protocol. That's used in some senses for miscellaneous messages and for protocol expansion. I'm not going to go into that in detail in today's webinar. But just wanted to note that does also have a credit exchange mechanism associated with it. So I'll move on now to talk a little bit about the message formats. I'm not intending to go into these into a great deal of detail. I just really wanted to give you a feel for the sorts of message formats, to show the types of fields that are included, and primarily to show that they're not particularly complicated in terms of the formats that are used. So I'll just use 2 slides, one covering the reads and one covering the writes. You'll see lots of common themes between them. So just starting off looking at so this first slide is showing a read request message and obviously a read response message. Obviously for reads, the request message is much smaller, just 12 bytes compared to the response, which is 68 bytes. Obviously it's compressed down on the slide. But they both have some standard message headers at the top. So there is a message type field, and that's differentiating between these reads, requests, and responses, and also between Snoop requests and responses. So that primary message type. There's a message length field, and that's just simply defining the length of this message. We'll see later on how that might be used when multiple messages are put together in a packet. And then, most importantly, is the transaction ID. So there's just a single transaction ID that is selected by the requester. That transaction ID is returned in the response. The responsibility of the responder to give that identical transaction ID back, and that's how the request is tied up with the response, how the two are associated with each other. And you'll see that those fields are common to all of the messages. The other fields, well, they're not necessarily common to all of the messages. There's certainly a theme running through them. So in most cases, you'll see an opcode field. So in terms of the read request here, the opcode field is saying things like whether or not it's a read or write, an atomic or a dataless, and also all of that information about the different types of read request and write request that we saw earlier. The request attributes are used when it's things like whether or not there's different sizes of transaction or different ordering requirements or different memory types. That's all communicated in the attributes. And of course, the primary field here is simply the address. It's a 52-bit address that's sent in the request. It is possible to send higher order bits, and also when needed, you'll notice that it's a cache line address that's sent here. So when needed, lower order address bits can be sent, and I'll show you that in a couple more slides' time. And there's also some other fields, so secure and non-secure address spaces are supported, and a QoS field if needed. So in the response, we have by far the majority of the response is the data itself, but we also have some attributes. So for things like whether or not clean or dirty data is being passed, or possibly whether the cache line state indication being provided, then that's given in the response attributes. So I'm moving on to talk about the write transaction message format. So as you'll see, very similar. The primary difference here, of course, is that the write has the data associated with the request. So that's all put together in a single message. In this example here, I've actually shown the byte enables in the data. For a cached line sized access, the byte enables are not included when it's a write to a full cache line. But there are cases where those byte enables are included. So just for the purposes of this example, I've included them. And then obviously for every write request, there is also a write response message. And that's shown as just a small response message, and it indicates that the write transaction has been passed on downstream to the next agent. Okay, so I'll just touch briefly on the extension fields that are used. So this partly touches on some of the topics I was mentioning on the previous slide. So extension fields are used to add additional information into a message when required, but it's for information that is not included in every message. So a single bit is used to indicate when an extension field is present. If I just quickly flick back to the previous slide, you'll notice in the very top left-hand corner there's a single extension bit. So every message has a single bit, and if that's set, that indicates there is an extension field, and then each extension field itself has an extension bit to indicate whether there is a further extension field present. 3 bits of the extension field are used to indicate the type. There's currently 4 different extensions defined, so there's room for more to be added as well. but the majority of the extension field is available as payload for whatever is the purpose of the extension. So the extensions currently defined are, the first one is for source and target agent ID replacement. Talk a little bit about that in a later slide, but also for higher order address extension as well. The next one that we have is used for lower order address bits, where we're doing sub-cache line accesses. If the offset is not 0, then the lower order address field can be provided. And there's also some opcode extension capability in there. There's an extension field that's defined purely for user signaling, and that's essentially free form in terms of how that's used. And then the final one is an extension field that's used for poison and or error signaling. So again, that's not expected to be a common case that field's used, but obviously there are cases where poison and errors need to be indicated, and that is the purpose of that extension field. So I'm getting nearly to the end now. So I'll just talk briefly, a couple of slides about the C6 packet format. So first thing to say is that I've talked a lot about different messages within C6, as you've seen, request messages, response messages. And actually, when we're sending these messages across a PCIe transport, we can put lots of messages together into a single packet. The packet has a packet header. What's shown in this diagram is what we refer to as a PCIe compatible header. So you'll see there's 12 bytes that those familiar with PCIe will recognize. And then there's also 4 bytes that include C6 specific information, and namely that is the source ID and the target ID. And also, I talked earlier about piggybacking credits, and this is where the credit is sent. The piggyback credit is sent in the packet header. And as the colors on the diagram attempt to illustrate, each packet can actually contain multiple different messages. So the default assumption is that all of those messages are going between the same source and target ID pair. So as the diagram illustrates the PCIe compatible header, there is also an option for an optimized header. If it's known that both sides of a given link are C6 compatible and they both support the optimized header format, then we can reduce that header down to just a 4-byte header, which essentially contains the same information, the credit, the target, the source. It will also contain a length field as well, a packet length field as well in there. And that's an optimization that can be performed. So there are a couple of packet optimizations, and this is used to make more efficient use of the packets, to amortize the cost of the packet header. So one of those is chaining. So chaining is used where we have multiple requests that are targeting sequential address locations. Where we have that, we basically have a dedicated opcode that says that a transaction is to a sequential address. That means it's sequential to the previous request in the same packet. And it removes the need to send the full address. So obviously that saves a number of bytes in the request. The other optimization is to do with putting messages that are for different source and target ID pairs all within the same packet. As I mentioned on the previous slide, that we effectively have a default source and target pair for all of the messages in a packet. It's possible to override that using an extension field for any given message in a packet, and therefore we can combine messages which have different source target pairs all within a single packet. So at that point, I've talked you through much of the protocol. So I've gone through an overview, starting off with an overview of coherency in general and some examples, talking through the cache states. I've talked through each of the different agent types. so the requesters and all of the different request types that they can issue. I talked about the home node and how it's responsible for maintaining control of cache states and for snooping. And I've talked a little bit about the topology, the way that routing is done, and the crediting that we use. And then finally, I talked about the message formats and how they're all put together into packets and the packet formats that we use. So I hope that's a useful summary of the protocol. Obviously, it's not been possible to go into to every detail, and there will certainly be more detail that is available in the specification itself. And I encourage you to look at that and dive into that further detail. And also, there's further webinar sessions to follow on other topics related to the protocol. So some of the other layers of the CCIX protocol, the CCIX framework that were mentioned at the start. And so both down at the transport and the file layer, and also up at the software layer, there'll be sessions on those. So with that, I'll conclude this part of the webinar, and I guess I'll hand back to Matt, who will coordinate the next section. Is that correct?
Yeah, thank you, Bruce. We're going to go ahead and open it up to questions, and if you have a question on anything that Bruce presented or that Millind discussed early on, go ahead and submit those via the chat window there, and I'll go ahead and read those to everyone, and then I'll let you guys decide who would be the best ones to answer. So if you have a question, go ahead and send that preferably to the entire audience, and we'll go through and answer those questions. I do want to also mention, while we're waiting for questions to come in, I wanted to mention that we will be posting this slide deck to the member area on Causeway. So if you have your membership and are able to log into Causeway, we will be making this available by the end of this week. Gentlemen, I'm going to open you up, and if there's any additional information that you would like to share, we'll go ahead and have you do that, or we'll go ahead and wrap up.
I think I'm fine from my side. Yeah.
Okay. And Bruce, anything else in closing?
No, nothing else from me. To everybody for their time today.
Okay, and let me see. I'm getting a couple questions here. Just a moment. Okay, so can you address the address translation management? For example, the TLB for address translation to be performed using PCIe ATS.
Okay, so maybe I'll just start from saying a few words on this, and then maybe Millind will join in as well. So yes, I mean, I think that the question's almost answered itself. The expectation is that when we are using PCIe as the underlying transport, that existing PCIe ATS mechanisms will be used to obtain translations. CCIX as a coherency protocol does work on the physical addresses, so that's required in order that the addresses that are stored in the caches, the same address that's held in the cache is also used by the Snoop, and that's done in its simplest form by using physical addresses in both directions. So yes, PCIe address translation services are used in order to obtain those translations from virtual to physical addresses.
Yeah. One thing I think I'll just add is, so for coherency protocol, the desired attributes are beyond what ATS today or PCIe by default supports. the attribute that PCIe supports is only Snoop or no Snoop, which is for IO coherent traffic. But for C6, there are a variety of attributes that are desirable, like allocate, and then allocate in the last level cache or not, basically, write back attribute, so on. So there is an active, we have come up with enhancements to that essentially ATS to support additional attributes, and there is the ACR currently submitted to PCIe, in regards to this as well. Yeah, but the CCIX spec defines these additional attributes capability for the ATS mechanism.
Great, thank you. Here's another question. Do we need all 3 agents on every node on C6?
Okay, so good question. And sorry for not highlighting that at any point, but so the answer is that we don't need all 3 agents. In fact, it's possible to have a node that has just request agents. Likewise, it's possible to have a node that just has home agents or just slave agents. So pretty much any combination of those agents is permitted.
Good. Looks like one final question here. How do you resolve loops during enumeration?
So I mentioned this briefly when I was talking about topologies. So I think what the question is referring to is how do you make sure that the routing is set up in a fashion that avoids loops? And that was one of the reasons for highlighting that some of those known good topologies, because for those topologies, we know that there are predefined routing algorithms that will avoid loops. So I won't attempt to talk through those algorithms today. I mean, they're actually relatively simple, but I won't attempt to talk through them in detail. And it may well come up in the software session, which talks about the enumeration process. But effectively, yes. So just recapping, for a set of known topologies, we know which routing algorithms avoid loops. And as I said in the presentation, it is possible to have other topologies, but it's necessary in order to do that, in order to ensure that the routing is done in a loop-free fashion.
Okay. In PCIe subsystem, config access are used for enumeration. Is there a similar mechanism for configuration management?
Okay, so I can take that one. Yeah. So essentially, the process of discovery is this: that we do utilize PCIe for discovery process. So C6 is defining a configuration space for C6 components, which as DVSec configuration space. So this is consortium defined DVSec. So basically, PCI standard allows you to extend the configuration space in a class of configuration space options called DVSec, and this is designated vendor specific extension configuration space, and we have come up with a way to determine to recognize that this DVSec is really specifying configuration for C6 components. So now you can imagine that essentially firmware discovers on a per port basis is discovering this is a PCIe device, it's a PCIe endpoint, and then from there is discovering that how many functions there are, and so on, and then it discovers that our DVSec space is going to be tied to function 0, right, of any of the ports on the device. So it will discover that, oh, for this function 0, you have a DVSec space defined. Then there is a specific way to determine that this DPSec really is specifying C6 components, right? So each of these components, RA, HA, and SA, they have their capability, configuration, and status space that is now accessible to the firmware. It walks through the space and essentially configures the routing tables, SAM structures, other capabilities, other configuration options, and so on. And at that point in time, the firmware host side starts to build up the notion of that here are the endpoints that have C6 capability, here are the types of agents they have, here are the routing options or connectivity that we have, and then from there starts to configure topology and populates it up to the operating environment.
Thank you, Millind. Looks like one final question here from everyone. It's with regard to topologies. Are there topologies like full mesh and array in which you can have multiple paths to each one from RA to another one?
So within the routing process, there will effectively be only one route that is defined. If I take as an example a request agent to a home agent, then there will, for a given address, there will be just one route that is defined between that request agent and that home agent. It's important that there is just one route defined because in the reverse path, the Snoops that are traveling in the opposite direction to requests need to traverse the same path. Although it is maybe worth saying that I haven't talked at all in the presentation about port aggregation. I don't know, maybe Millind, if you want to talk a little bit about that.
Yeah. So there is, as we mentioned earlier, that C6 is really trying to address, multiple limitations that exist today when you connect accelerators with the host SoCs or connect the accelerators together. One being the speed, other being the bandwidth, other being the data sharing paradigm. So when it comes to the bandwidth, one of the limitations is that the number of lanes that you can have on an interface today is limited to 16 lanes typically, right? I mean, basically PCI is 16 lanes, right? The second observation is that as you go to higher speeds, like for example, 25 gig, 32 gig, and then 56 gig beyond that, naturally you start to get to a point where even to have a single controller that can deal with 16 lanes gets harder and harder, right? So then essentially this issue needs to be addressed. How do I have higher speed lanes? And at the same time, how I have higher bandwidth connectivity that goes even beyond 16 lanes capability, and do it in a transparent fashion to the protocol that overrides over this transport. And the way that is done in C6 is this notion of the port aggregation. Essentially, what happens is that between a path from RA to HA, you have a request that's going out, a message that's going out. Now, essentially, at a transport level, from top level, you just say this address is going to an HA. These are on two different components. But at transport level, what you want to be able to do is load distribute your access across multiple controllers. And that's the notion of port aggregation, where there is capability defined in your SAM structure. You can specify that for this address range, you actually can stripe or you can do load distribution based on some hash functions across multiple controllers. So in that sense, you do have paths, but for a given address, that a given address will go over only one transport connectivity, essentially.
Very good. Well, we'll go ahead and wrap this up. And for those of you who are able to join us again next week, we appreciate you taking the time. Thank you for everyone who joined us, and big thank you to Bruce and Millind and Phanindra for being willing to answer some additional questions. Thank you very much.
Yeah.